Hello dear students, welcome you all. In this lecture, I am going to take up the next section of the question paper of 2019, subject mechanics. I have already solved the section A and section B from this question paper. So now I am coming to section C, right? In section C, the question number 4 is state Kepler's law of planetary motion, prove any two of them. Right. So this question is basically from the chapter gravitational force and inverse square law of force. Right. And this is the most important question that is usually asked in the exam. So first of all, I'll solve this question. The question is state Kepler's law of planetary motion, and then I will come to the proof any of two of them. Right. So as far as Kepler's law of planetary motions are concerned, we know very well that these laws were given by Johannes Kepler. Johannes Kepler in 1609, right? And these laws govern the motion of the planets around the sun. They actually describe the different properties of this motion or working of the solar system. There are three laws. The first law tells us about the orbits. We call it as a law of orbits, right? So according to Kepler's first law, all planet moves around sun in elliptical paths with sun at one of the focus of the ellipse. So this is the first law. This is a statement. All the planet moves around the sun in elliptical paths with sun at one of the focus of the ellipse. Second law, we call that law as a law of area, right? So according to second law, the areal velocity of the planet around the sun is always constant. What is the meaning of it? The meaning is very simple, that if we draw a vector from the sun to the planet, then with the motion of the planet around the sun, this vector will traverse equal area in equal interval of time. We call that as areal velocity. So the areal velocity of the planet around the sun is always constant. Velocity of the planet is never constant. Don't confuse in that. Velocity of the planet around the sun vary according to its position, but the areal velocity is always constant, right? So this is the law of area, and this is the statement of this second law. The third law is known as the law of time period. So according to third law, the time taken by any planet to move around the sun is directly proportional to square of that time, right? Is directly proportional to the cube of semi-major axis of the elliptical orbit of the planet, right? What does that say? According to third law of Kepler, the square of the time period of the planet around the sun is directly proportional to the cube of semi-major axis of the elliptical path of the planet, right? So these are the statements of these three laws, right? Now I am showing you one animation. From there you will get the clarity of these three laws, right? Let's come to it. So you can see now here I am coming to the first law. First of all, so you can see here, this is the elliptical path of the planet. This is sun. This yellowish wall is sun, and these are the two foci of this elliptical path. Sun is present at one of the foci. This is the definition of the first law. All the planet move around the sun in elliptical path with sun at one of the focus of the this elliptical path. So you can see here this bluish arrow points the gravitational force of these two bodies. This is a planet. It can be Earth, it can be Jupiter, it can be Mars, any planet. This is the direction of the velocity vector of this planet, right? Now I am showing you. You can see the planet is moving around the sun. You can see here how the direction of the velocity vector changes and how this gravitational force between these two bodies act, right? So this is the first law. You can clearly see the planet is moving in elliptical paths with sun at one of the foci. The one more thing that you can observe here, that as the planet is approaching the sun, right, its velocity is in, let's see here, now it is approaching, its velocity is increasing, right, 27, 28, 34, then it is, when it is going away, then its velocity is decreasing. You can see when it is at farthest distance, this point, right, then its velocity is minimum. What when it is at the closest point, right, then its velocity is maximum, right? As it is coming toward the sun, its velocity is increasing. But as it is going away from the sun, its velocity is decreasing. But the aerial velocity, that is the second law, we will see here. So you can see now I am coming to the second law. This is the second law. Now you can see here, this is the planet that is moving around the sun, you can see, and this is the diagram that is showing the area traversed by this vector. This is the line that joins the sun with the planet. Now this line is, this is the area in given time interval. So according to second law, if I am taking the time interval of suppose 1 hour, then in 1 hour this is the area, then in the next 1 hour the area will be different, but the second law states that this area is always constant. You can see from here, right, this area in all intervals, you can see we are taking 4 intervals here, right? I am dividing this entire area of this path in 4 intervals, this one first, second, third, fourth. So you can see all these areas are equal. This is clearly showing you this entire elliptical orbit is divided into 4 parts, 1, 2, 3, 4, but all the areas are equal. So this is the second law of Kepler, right? And according to it, the aerial velocity is always constant, right? Now I am coming to the third law, right? Third law is this one, right? You can see from here. According to third law, this is the semi-major axis. You can say it is E, and the time period will be the time taken by the planet. You can take it here, right? Let's start from this point. I'm starting from this point, right? So yes. Now the time taken by the planet from going from here and to there and then coming back to here, the square of this time period will be always proportional to the cube of this semi-major axis. This is the meaning of it. You can see here. This is the graph, right? T versus A cube. So this is the third law that I told you, that the square of the time period is always proportional to the cube of a semi-major axis. So as it is shown here, T versus, this graph is basically T versus A cube, but we know that according to this third law, T square is directly proportional to A cube, right? So this is about the animation that clearly explain these 3 Kepler's law. Now I am coming back to the mathematical part of these 3 laws, as we have been asked to prove any 2 of them. So I am coming to the proof of these Kepler's law, right? So let's drive the first law of orbits. So we know very well that general equation of conic is 1 upon r is equal to 1 upon L, right, into 1 plus epsilon cos of theta minus theta naught. This is the general equation of a conic section, right? Here L is semi-latus rectum, epsilon is the eccentricity, theta is the angle at any point, and theta naught is the initial angle, right? R is the radial vector. So from here I get R is equal to L. If I rearrange this equation, L upon 1 plus epsilon cos of theta minus theta naught. This is what I got from here. Now this is equation number 1. Now I am applying different conditions on this equation. we know very well that this factor cos theta minus theta naught, it will be a minimum when theta minus theta naught will be equal to pi, right? Because cos pi is minus 1, so this factor will be minimum in that case. And when it is minimum, we can say that theta 180 degree will occur when this r will be maximum, when the planet is at the farthest point. You have seen already there that if this is the, let me draw the elliptical path. This is the elliptical path, right, for understanding, right? This is one focus, this is another, and when the planet is at, I am showing you, I am telling you that if the planet is at this point, right, then in that case the angle that will be equal to 180 degree, right? So that's what I am saying, that when the angle is 180 degree pi, then this r is r maximum, right? So it means if I took theta minus theta naught is equal to pi, then r maximum I got is equal to L upon 1 minus epsilon, right? So this is r maximum from here. Similarly, r minimum. R minimum means when this thing is a maximum, and this is maximum when theta minus theta naught is equal to 0. So theta minus theta naught is equal to 0 means at this position, right? The planet is here. At this position, theta is 0 degree, right? We are starting from here, right? In that case, theta is 0, cos 0 1, so r maximum 1 L upon 1 plus epsilon, r minimum, sorry. So these are the two equations, equation number 2, equation number 3. Now I got r minimum and r maximum. We know very well, if I add up these two, r maximum and r minimum, then what I will get? I will get 2a, because in centricity is major axis is a, right? So a plus a, 2a. So if I add up r minimum and r maximum plus r maximum, that will give me 2a. So let's add up these two. So it give me a is equal to 1 by 2 into r minimum L upon 1 plus epsilon and plus r maximum L upon 1 minus epsilon. So these are the two terms that I put up here. Then after solving it, I will get a is equal to L upon 1 minus epsilon square, right? Now let's find out the value of epsilon, right? We know very well, we have learned about the expression for the eccentricity in this chapter. So if I go to that, then we know very well eccentricity epsilon is equal to under root of 1 plus 2 e L square upon mu k square. Here mu is the reduced mass, k is the force constant, L is the angular momentum, E is the energy. So epsilon square, it gives me 1 plus 2 e L square upon mu k square. So from here, what I got? I want 1 minus epsilon square. So 1 minus epsilon square is equal to minus 2 e L square upon mu k square. This is the value of 1 minus epsilon square that I am going to put here. Let this is equation number 4, right? Now I want the value of L, semi-latus rectum. So we know very well that L, the value of L in this particular case is L square upon mu k, right? So I am going to put equation number 5, this one and this one this one and this one, right, here in this equation. These two values I am going to put. So then after putting, what I will get? I will get the value of A. A is equal to L. L means L square upon mu k into 1 upon this one, 1 minus epsilon square. So it will become mu k square upon 2 e L square and negative. This is what. So when you will look at L square mu k square k. So what you got? You got minus k upon 2E. So this is the expression that I got from here for A, right? So if I rearrange it, then what I will get? I will get sorry, energy is equal to minus K by 2A. So if the energy of the planet, total energy of the planet is negative, what does it means? We know from the conditions that if the energy is negative, then it means the orbit of the planet is elliptical, right? So this proves that all the planets move around the sun in elliptical paths, right? So this is the proof of first law of Kepler. Now I am coming to the second one, right? According to second law, we know very well that the aerial velocity of the planet around the sun is constant. So you can say here I have drawn the orbit of a planet. This is the position of the sun. You can see here. This is the position of the planet S1. This is the second position of the planet when it is moving in this direction, right? S2. When it was here, its position vector was r. The displacement from this point to this point is dr, and this position vector from this point to S2, it is r plus dr. Obviously, let this is angle theta, right? This is semi-major axis and this is semi-minor axis. Now, if we look at this vector SS2, then this vector is r plus dr. Right? Now, let's look at the area of this vector. This sector. What is the area of this sector? I am calculating the area of this sector of this, elliptical path. Right? So obviously, the area dA. Let this area is a dA. It will be this distance r multiplied by 1 by 2. Sorry, 1 by 2 r into this. Distance, that is dr, right? This is the formula of calculating the area of this sector. R, this position vector from here to here, and this distance dr, right? So 1 by 2 r cross dr. Now dr, it is the displacement from this point to this point, and dr, if the b is the velocity of the planet at this point, suppose, right? B is the velocity, right? Then obviously this distance dr will be equal to velocity multiplied by time v dt, right? So I am putting dr, replacing dr by v dt. So what I will get? I will get dA is equal to 1 by 2 into r into dr means b dt. Dt is taken toward this side, so I got dA upon dt is equal to 1 by 2 into r cross b, right? So here I am multiplying this expression in the numerator and denominator by mu. So it becomes mu reduced mass, right? So now it becomes r into, let it is mu reduced mass multiplied by velocity divided by mu, 2 mu, right? 2 taken from here. Now this is mass into velocity, this is momentum, so it becomes r cross p divided by 2 mu. Now what is r cross p? It is L, angular momentum, L upon 2 mu. So dA upon dt, it becomes dA upon dt is equal to L upon 2 mu. We know very well that when a body moves under the influence of a central force field, then its angular momentum L is always constant, and mu is already constant, it is the reduced mass. So when L is constant, it means the dA upon dt, it is always constant. So this is the proof that the area, what is dA upon dt? Area traversed per unit time, that is aerial velocity. So this proves that the aerial velocity of the planet around the sun is always constant. So this is the proof to the Kepler's second law that was asked in the exam, right? So now this question is over. First of all, we wrote the definitions or statements of these three laws. Then after I proved first and second law, right? So this is all about it. Now I am coming to the second part. This is reduce a two-body problem to an equivalent one body problem, and hence drive the equation of motion of a reduced mass, right? So I am coming to this question now. So I am coming to the second question. You can see here the question was reduce a two body problem into equivalent one body problem and drive the equation of motion for the reduced mass. So here you can see this is question number B part of that question. I think question was question number 4, right? Number 4, B part. So here I have taken two bodies of mass m1 and m2. These two bodies are interacting under the influence of central force field, right? And here I have taken the force as gravitational force. This is the coordinate system you can see here. Now, let at any time this body is present at this position having position vector r1. This body is at this point having position vector r2. Now, F12, this is the direction of the force exerted on the body 1 by body 2, because body 2 is pulling this body toward its side, so direction of force is this. Similarly, F21 is the force on body 2 due to body 1, and the direction is in this side because this is pulling this body toward its side. If I look at the position vector, this r from here, then it will be r2 minus r1, because this plus this is equal to this. So in that case, it will become according to triangle law of vector addition, right? According to triangle law of vector addition, this vector plus this vector, this will be equal to this vector. So this vector is equal to this minus this. So I have written it here. But remember, I am looking from this point. So if I write down the equation of motion, not equation of motion, but gravitational law, right? Then gravitational force on body 2 due to body 1, F21, we know very well it is G m1 m2 upon r square, or we can write r cube, that is r2 minus r1. This is the distance between these two vectors, these two positions, r2 minus r1 cube into vector r2 minus r1. This is the according to Newton's law of gravitation. We usually wrote it as F is equal to G m1 m2 upon r square, but in vector form we can write it in this way also, right? Now this is that equation number 1. Similarly, I can write down the expression for F12. Now when I am writing down F12, then I have to look from here. In that case, what r will become? In that case, if I am looking from here, r will become r1 minus r2, right? Because now when I am looking from here, this will be the direction of this vector in that case. This plus this is equal to this, right? And this is equal to this minus this. So now in that case, F12 will be equal to Z m1 m2 upon magnitude of r1 minus r2 vector cube into r1 minus r2 vectors, right? That it is equation number 2. Now if we look at the magnitude, we know magnitude of this vector is always equal whether we are writing r2 minus r1 or we are writing r1 minus r2. No change. But if we look at r2 minus r1, then obviously it will be the negative of r1 minus r2, right? So here in equation 1 and 2, we can see that r1 minus r2 vector magnitude is always equal to vector r2 minus r1 magnitude. Magnitude no difference, sign will be different, but the sign is reverse. It means I can say F12 is force is negative of F21, right? So this is the meaning of it. These two forces are in opposite directions and their sum is always equal to 0, right? So this is equation number 3. Right? Now let's write down the equation of motion according to the Newton's second law. We know from the equation of Newton's second law, F is equal to m d square r upon dt square. So if I put the value of F for the first body and for the second body, then I will get the equations F12 will be equal to m1 force on body 1 d square r1 r1 upon dt square, right? This is for the first body f1 2, right? Similarly f21 f21 that will be equal to m2 d square r2 upon dt square. Here it was r1 f12, so I think I have mistaken here. It will be, because we are writing the equation of motion of the first body d square r1 upon dt square, and it is d2 r2 square d square r2 upon dt square, right? So these are two equations that I wrote here. F1 2, let it is equation number 4 and it is equation number 5, right? Now from equation number 4 and 5 I can modify them. So I can write d square r1 upon dt square is equal to f12 vector upon m1. Similarly d square r2 upon dt square vector form is equal to what? Is equal to f21 vector upon m2. So these are the two equations. Now I have, so subtracting this equation, let this is equation number 6 and equation number 7. Subtracting equation number 6 from equation number 7, right? So what I will get, I'm writing it here. I will get d square r2 upon dt square minus d square r1 upon dt square, that is equal to f21 upon m2 minus f12 upon m1, right? This is what I got from here. Now we have proved here that f12 is equal to negative of f21, so I can put it here, right? And I can replace even f12 by f21. Let me do it in this way. I am replacing it. F12 is equal to now f21, and I will get plus sign here. Now this is what I got from here. So I'm now going to the next page. Now here I can take common d square upon dt square r2 minus r1. So in that way, next page it will become d square upon dt square into r2 minus r1 vector is equal to f21 vector upon m2 plus f12 vector upon m1, right? So r2 minus r1, let it is equal to r d square upon dt square vector r, and let it becomes f21 is common, so 1 upon m2 plus 1 upon m1 f21. It was f21 here, I have mistaken, so let's correct it. F2 sorry, f21. So now this is what I got from here. So I can replace this term as 1 upon mu, right? So in that case this will become d square r upon dt square, that is equal to 1 upon mu into f21. So I can further simplify it. It will give me f21 is equal to mu into d square r upon dt square. So here mu is called reduced mass of the system. So now you can see from this equation that instead of having two equations of motion, now I have only single equation of motion, and this equation of motion is basically the equation of motion of the reduced mass. So we can say the problem of two body is reduced into problem of one body, and we call it as the reduction of two body problem in one body. F is equal to m into a. Earlier we have two equations. I am showing you these two equations. Let me check it. Is this one? Let me check it. These are the two equations that I am talking about. Earlier I have two equations. This equation number 6 and equation number 7. So I have two equations of motion for the two bodies. Even you can call these equations 4 and 5 as the same. But now these two equations are reduced into one equation, right? So this is known as the reduction of a two body problem into one body problem. So instead of solving two differential equations, we will go for the solution of only this differential equation. So this is the answer to this question that was asked in the question number 4 part B. So now the question number 4 is over. In the next lecture I will go to question number 5, right? So thank you very much.